Graphs can be transformed using just a few rules rather than a bunch of different calculations. These are the rules that you need to have with you at all times when transforming graphs. Start off with vertical transformations, then we can have horizontal transformations, and then we can also have a reflection. So taking a closer look at each of these categories, looking at the vertical shifts, we have y equals f of x plus c, or y equals f of x minus c. So we have the function there intact, and then we just add some number to it. C is always representing just some number. So y equals f of x plus c, the description of that is to raise the graph of f by c units. Y equals f of x minus c, the description would be to lower that graph of f of x by c units. Next we have horizontal shifts. Y equals f of x plus c, and I realize it sounds very similar, but by basic order of operations, this is a very different statement than up here where the plus c is on the outside of the function, and down here with the horizontal, the plus c is on the inside of the function. The plus c shifts the graph of f to the left c units. Y equals f of x minus c shifts the graph of f to the right c units. A reflection about the y-axis, and a reflection is exactly that. Imagine that a mirror is being held over that particular axis, and the function or the graph is seeing its reflection in the mirror. So to reflect about the y-axis, the equation would change to be y equals negative f of x, and that's a reflection over the x-axis. A reflection about the y-axis would be y equals f of negative x. The only other two that we address here are vertical stretching and shrinking and horizontal stretching and shrinking. So for vertical stretching, you're going to have a multiplier. So c times some function. Where c is bigger than 1, you're multiplying the y coordinates by c. So the x coordinates are staying put, the y coordinates are getting multiplied. When that c value is between 0 and 1, that's going to be a shrinking. Horizontal stretches also have a multiplier. The difference is the placement of that multiplier. So if you have a vertical shrink or a vertical stretch, that multiplier is on the outside of the function. If you have a horizontal stretch or shrink, that multiplier is right in the middle of that function. So when you have a horizontal stretch, you are dividing, or shrink, you are dividing the x coordinate by c. Seems like a lot, but let's break it down. Looking back at the vertical and horizontal. For vertical and horizontal, in both cases, you're adding or subtracting something. That's how you know it's going to be a straight side to side or up and down shift. For a reflection, there's going to be a negative multiplier. And for a stretch or a shrink, there's strictly a multiplier. Okay, so stretch and shrink are just going to have a multiplier. Vertical and horizontal shifts just have plus or minus. And then the negative sign is going to be a reflection. Let's put a picture to that. It makes much more sense. So if we consider the function f of x, this is just a random function. It doesn't matter what the equation is. We're not going to need the equation, so we're not going to talk about it. This is just a random graph, and we have the points labeled A, B, C, D, and E. And we're going to use this graph to do some transformations. So given the graph of f of x, determine the graph of g of x equals f of x plus 3. So starting with that f of x that we had on the previous slide, and let me just make a side note here that f of x can change. This is not the only f of x that ever is. It's just for these next few examples, this is the f of x that I am using. So this is the same f of x that was on the previous slide, and that f of x plus 3, so that plus tells me it's either a horizontal or a vertical shift. The fact that the plus is on the outside of the function leads me to believe that this is going to be a vertical shift. Okay? So this is going to be a vertical shift up 3 units. So because we have a plus there, it's going to be a shift up. So to see what the graph looks like, every single point, so this point A just moves up 1, 2, 3 points, and you can see this is where the A is now. The B moves up 3 points. The entire graph, almost as if it was on a rail, you're going to pick it up and shift the whole thing up 3 places. So if you trace each point, point A, 3 places, B, 3 places, etc. So very literally, the entire graph just shifts up 3 places. To see the difference, let's use the same f of x and determine what the graph of g of x equals f of x minus 3 looks like. Remember back here, we had f of x plus 3, and that plus was on the outside of the function. Now we have a minus 3, but it's inside as part of the function. This tells me it's going to be a horizontal shift. That minus tells me it's actually going to be a shift to the right. So this is my basic parent graph, f of x. My description of the change is that it's a horizontal shift 3 units to the right. And here's what it's going to look like now. Every single point, starting with point A, has shifted 1, 2, 3 places to the right. Okay. Same thing. It's very literally being picked up and moved 3 places to the right. The entire graph. It maintains its position. It maintains its shape, I should say, but it's just moved 3 units to the right. Next we're going to use the same graph of f of x, and we want to know what g of x equals negative f of x looks like. That negative sign tells me that I'm going to be dealing with a reflection. So it's going to be a reflection over the x-axis because that negative sign is on the outside. If that negative sign had been on the inside of the parentheses, that would have been a reflection over the y-axis. So this function is going to be using the x-axis as a mirror and seeing itself in the mirror. So this is a reflection. I like to visualize this as a piece of paper. If this was a piece of paper, you could fold it in half along the appropriate axis, in this case along the x-axis, and that graph would just literally jump to the other side of the paper. Now we can take the same f of x, and now we're going to transform it in 2 different ways. So we're going to take g of x equals f of x plus 2 plus 3. So we have a horizontal and a vertical shift happening here. So we're going to take first the horizontal shift to the left 2 places and a vertical shift up 3 places. And we can do this all at once. We can move point A to the left 2 units and up 3 units all at once. I'm going to start with E here just because I'm going to run out of room with the A. So starting with E, we're going to go to the left 2 units and up 3 units. And you can see that the point E is now at 3, 2. Every single point just follows along. So the entire time that graph is maintaining its shape, it's just getting put in a different place on that XY plane. Next we have a graph of g of x equals f of x g of x equals 2 times f of x. So now we have a multiplier. So the multiplier tells me that I'm either dealing with a stretch or a shrink. And again, it matters the value of that multiplier, which in this case is a 2. 2 is bigger than 1. And it also matters if the 2 is on the outside of the function or if it's on the inside of the function. So the placement of the 2 tells us that we multiply the y coordinates by 2, making this a vertical stretch. So in this case, it helps to make a table, start with the x and y values that are in the current f of x. So point A is at -3, -1. Point B is at -1, -2. Point C is at 1, 0. D is at 3, -2. And E is at 5, -1. The rule in our graphing transformation chart tells us that we multiply the y coordinate by 2. So we're going to take y multiplied by 2, which gives us a new ordered pair to graph. So point A now has the ordered pair of 3, -2. Point B is -1, -4. Point C stays the same because anything times 0 is still 0. D moves to 3, -4. And E moves to 5, -2. So you can see when it stretches, it's almost like taffy. It's being stretched out. It still kind of has the shape, it's just a stretched out version of it. So it's nice to have these rules on hand to transform graphs. It's almost, dare I say, a little bit fun.